When I first introduced the molten globule, I did it from the concept of hydrophobic collapse, which is still true. But now I'm going to look at this in a slightly different way. What happens when I'm actually bringing things together, and what is the influence of the protein actually being a chain? It turns out that this chain literally just means that the protein is a polymer, just like a piece of plastic, right? But this does not have any of those nice protein properties. It doesn't really have any well-defined function or packing or anything. It's kind of boring, so let's throw it away. We can study this just with hand waving and showing you roughly how the energy or entropy should behave. I'll get to that in a second. So if you don't want to follow the derivation, just forward a bit. But those of you who are interested, I'm going to write down a few things. So one case is that I simply have beads that are not connected. And then I want to add a new bead to this system. And I'm just going to need to invent a few things here. So I will say that that new bead is going to have the energy epsilon. And it has the volume omega. You can use any numbers you want. And that means that if I have a total number of particles n and a total volume v, some sort of volume in this system, v and n, that means that I can say that the density I have is rho, and that's going to be the number of particles multiplied by the volume of each particle divided by the total volume, right? So that will go from 0 to 1. When it's 1, I'm crowded in here. So what happens when I'm adding one more particle to this? Well, when we're starting, the volume available, that's going to be the total volume divided by n particles. But some of that is going to be taken already, right? So the part that is taken is the number of particles I've already added multiplied by the volume per particle. So what should I write? Once I'm adding this new particle, I'm saying the volume, the available volume is roughly equal to the total volume available minus the part that I've already occupied, and then I'm dividing per particle. Again, volume available particle. That equals, if I use the expressions above, that's volume divided by n, 1 minus the density, right? Because the volume divided by n there minus omega divided by n, which is the volume divided by the density. Sorry, volume multiplied by density. And then I can use the volume multiplied by the volume there and dividing by the density. That's going to be omega divided by rho. So I can simplify this even further. That's omega divided by rho multiplied by 1 minus rho. And now all the large v's and the large n have disappeared. I only have to care about volume per particle and the density, which is a number going from 0 to 1 as I've been adding particles. This I can actually plot and see what happens. Why would we like to plot that? Well, there are two things we're interested in here, right? I would like to understand how the free energy is changing as I'm adding that particle. And god damn it, by now I hope what equation you should use. You should F equals E minus Ts. So we need to look at how the energy is changing and how the entropy is changing, right? But the entropy, that was just really the logarithm of the volume. So there are going to be two parts here. And I'm going to run out of space here, so I'm going to need to erase this. But if we look at the energy first, if I'm starting from some sort of number, for every particle I'm adding, I get epsilon. So the more particles I'm adding, the lower the energy will be. So it's some sort of density here. As I'm adding more particles, the density will just go down linearly. Boring, but simple. The entropy, on the other hand, this is going to be more complicated. let's plot it as a function of density. And I'm not going to be, so delta S is going to be the logarithm of this, but I'm not going to worry too much. If the density goes towards 0, this is going to be 1 over 0. So when the density here is 0, this is going to be a very large number, and the logarithm of infinity is still infinity. So there's going to be something up here that's very large, all the way up. As the density goes towards 1, well, eventually we'll say 0 here. I can't take the logarithm of 0, so I can't really get all the way to 1, but I could get so close that when the system is perfectly fact, there is only one way of organizing things. And that means that it's just one way of doing it, and then the entropy would be 0, right? So at some point the entropy is going to go to 0, and then there will be some sort of shape between them. And I was just guessing here roughly how it looked, based on the fact that I know that equation. If we now plot those two in terms of the free energy, F equals E minus Ts. It's going to depend a little bit on what the temperature is. So depending if the temperature goes from low to high, when the temperature is very low, well, when the temperature is low, that means that I don't have a whole lot of influence from the entropy term. The energy will dominate. You can actually show that you will end up with something that looks roughly that way. And then if I'm increasing the temperature a bit, it might start to look that way. And eventually, if I keep increasing the temperature, it's going to look something like that. So what do we say? Low T to high T. This is beautiful. We love this. This is a phase transition. Do you see here that at high density, this state is going to be best. And then at some point when we're changing the temperature, it's going to be better to jump over to the state of low density. And that's actually what happens. For instance, if a gas is undergoing a condensation or something. Plain and simple. In a system with some sort of particles that just attract each other, when they start to condense into a ball or anything that's making them attractive, it will undergo a phase transition. Cool. Now we just need to repeat this for the case when they are connected by a chain. But then I need to erase this first. But remember that plot. So if we repeat this for a chain, the first part is actually going to be easier. Now I have a chain here, and at some point we're adding one new monomer to this chain. And we want to investigate exactly the same thing, what happens here. So the energy is again epsilon. And then we have the volume omega. And we also have N and V, but I'm not going to use them. I'll save you some time there. The introductory part here is exactly the same as the volume available here is really going to be 1 minus the density, right? The difference though is that this particle I can't put anywhere. I can only place this in sort of small region that depends on the distance since the previous residue I added. So I can't add it to the entire system. So the available volume here is going to be roughly some sort of constant omega. Think of omega as the volume available around the previous monomer, multiplied by 1 minus density. And this just means that if I'm already crowded the entire system, I can't really add anything more. And when I'm starting out, the entire volume here is available. You can derive that properly the way I did it a few minutes ago. This looks almost that previous equation, but I don't have 1 over rho here. So if we just, that means that the entropy then, entropy equals K ln volume. And if we don't care too much about K and everything, that's going to be omega multiplied by 1 minus rho. But omega was just a constant. So if I plot this the same way I did in the previous slide, energy is going to look exactly the same. Goes down. Entropy, well, when when rho is very close to 1, I'm going to have the same shape there. Then it will reach one specific state. But when omega is 0, this is just going to be a constant. So I would go to some sort of constant value for the entropy there. It's not going to go to infinity. And what this means is that depending on temperature, you're going to get something that looks roughly like this, or like that, or maybe like that, where that is low and that is high. You see, it looks completely different, and in particular there is no phase transition here, which is horrible. We don't have a beautiful phase transition anymore. Let me erase this and draw the other plot right next to it so I can compare them. So just to recap, this is when we had a chain, and here's when we had a, should we say, a cloud. So in the case of cloud, energy looked exactly the same way. Entropy, on the other hand, looked like that, went to infinity, and F equals E minus Ts had a shape like that. So you actually had a proper phase transition. Or at a different temperature, it might look like that. The reason why this happens is that if you're in a cloud, in terms of entropy, the best possible state for all our molecules is to be almost infinitely far away from each other. If the volume is limited, I can't go there. But in the world, the further away you are, the more ways we have to organize. If you're in a chain, on the other hand, we're bound together. So there is an upper limit, and you really can't get further away. And it's really this upper limit that means that we don't have a proper phase transition. I can't get to the point where I'm infinitely far away. So what really happens in the molten globule is not that you have a phase transition. The phase transition happens here when molecules first don't interact at all, and then they start to interact, condense. In the chain, they are already interacting. They can't get out to infinity. So what happens when I form the molten globule is really that I'm kind of freezing it in. I wouldn't say freeze, but I'm starting to find some sort of local minimum, but it's continuous. And that's what happens in this hydrophobic effect. It's better, rather than being stretched out and have the hydrophobic interactions with water, the hydrophobic effects means that I collapse, and at most temperature that's going to be advantageous, but it's not advantageous in the sense of a phase transition. There is no phase transition when we're moving between coil and molten globule. But for proteins in general, the chain is imperative. If you were not a chain, for most combinations of amino acids, it would be better to just spread the amino acids infinitely far apart. And that would mean that it would be extremely advantageous to be in the completely unfolded state, right? And that would mean that you would need insanely good energies to ever make the folded state. So this chain aspect is kind of important for us, or being a polymer, that's important for us to actually be able to fold proteins in realistic time. But the chain per se does not make a protein. The chain just means that there is going to be an effect that we condense together, but there is no uniqueness here. There is no magic, there is no phase transition. That will have to come from elsewhere.